everyone. First of all, thanks a lot for inviting me to this talk. It's very exciting. I was a couple of weeks ago attending a meeting with NEC in Heidelberg, and they were speaking a lot of the things about this project, so it's very good to be here. And at the same time, apologies because I don't come from the 5G kind of environment, so I hope that this talk doesn't get a lot or out of the topic. So, first of all, just a bit of introduction about myself. My background is in computer science and mathematics. I studied in Universidad Autónoma de Madrid. Then I moved to Telefónica and Labs. I started working more in networking. I worked with the core network evolution people, so I was more focused in TLS kind of networks and multi-layer and multi-domain orchestration. And I was building architectures such as the path computation element or the application-based network operations. And then afterwards I moved to University of Bristol. I've been working there already for a couple of years, not yet, but almost a couple of years, and I've been working more in optical transport SDN, basically in open flow extensions for optical, in transport network virtualization as well, and in network function virtualization. And now these days, I've been as well collaborating in a project called Quantum Hub, trying to do a first approach for software-defined quantum key distribution networks. And a few slides as well of introduction about my group. We are currently 3 full-time academics. We are, well, I haven't met them all, but we are around 40 postdoc researchers and PhD students, and we are collaborating and working in different FP7 and FP20 and TSOC projects. And as research outputs from these last 5 years, we have around 150 journals, more than 250 papers in conferences, different invited talks. Well, our favorite conferences are ECOC and MC. We normally go there. We have some other papers as well, and some best paper awards, some contributors to standards, and 3 patents. And the main areas of research are, well, our group is basically an optical group. So in terms of technology, we are working with optical packet switching, optical bus switching, time-set optical networks. We've been working in some sort of virtualizable boundary variable transponders, and well, different technologies in the optical domain. We've been working as well in software-defined networking and network function virtualization. As well, we have a couple of projects, or 3 European projects working in different data center architectures, so for inter and intra data center. We are currently working, I don't know if as any of you are aware, we have like a big, I don't know if call it company or project, which is Bristol is open, so some of our guys, some of our researchers are moving towards doing research in for smart cities. And so we are working with big data, trying to do this kind of mobility awareness and handover, and working with different analytic platforms. And as well, we have now a really big EPSOC project called Tucan, and one of the things that we are trying to work with is our network convergence. So this is just another picture with the different research areas that we are working on. So here, I think that's not clear IoT and this kind of big data and smart city research, but virtualization, SDN, and this kind of things at this step. And about the talk, I want to talk mainly about, well, give a generic and incremental view of what has been the work of our group in network softwareization and as well in network virtualization. So I will start talking about software-defined optical transport networks, then give a first introduction about virtualization and the way we are approaching. Then the first approach, which was network slicing, and I will explain the differences between the network slicing that I've been listening to these days and the network slicing that we were doing at that time. Then I will move to virtualization in core and network networks. And as well, I will talk a little bit about virtualization in optical data centers. And I will finish the presentation talking about the Tucan project and some possible collaborations. So, software-defined network. When I was asked about how to present these optical software-defined networks, I started thinking first from the packet point of view. So, software-defined networks normally try to bring, of course, flexibility, dynamicity, this kind of thing. But one of the main concepts that SDN brings to the packet domain is programmability. And what programmability means in the packet domain. So you will have basically whatever packet device, let's say layer 2 switch, and you can program the switch in order to do two different things. One is change the behavior of the device itself, so you can set some sort of rules in order to do NATing, firewalling, or other kind of things. And at the same time, you can change the behavior of the flow. So you can inject VLANs, you can change maybe IPs, you can do different things with protocols such as OpenFlow. So in this sense, is an optical network programmable? I would say that no, but it's configurable. So what SDN brings to the optical network is flexibility, dynamicity, and have a common platform where you can actually manage everything, and as well bring some sort of advantages over traditional GMPLS-based networks by reducing the time of in the deployment of an network path, for example. So what is the work that our group has been doing? Basically, it has been OpenFlow extension for different kind of devices. So we started working now, as Reza mentioned yesterday, we have a company that is working as well in this kind of OpenFlow extensions. They moved to OpenFlow 1.4, but our group started working with OpenFlow 1.0. So we provided some sort of OpenFlow extensions for different devices such as optical version switch, like we have this Polaris company, for TIPS and Flexi, WSS, RODAMs, and other kind of technology as well. So I think we did extensions for NICTARs, for ISO, I think we did as well, OBS. And mainly we were modifying two different messages, which are the features reply and the flow mode. Actually, it was renamed to C-flow mode at the time. And as well, we've been modifying, it doesn't appear here, but some stats reply as well. So, and the main work, the way we are doing this OpenFlow enabled devices is building OpenFlow agents. So typically, all these devices will speak some sort of protocols like HCPI, Tier 1, or whatever it is. Then, on top of that, we will build some sort of logic in order to map the OpenFlow messages for whatever other kind of protocol. In this case, it's OpenFlow. We could have done with Netcom as well, but it was done with OpenFlow, and build this OpenFlow 1.0, sorry, with extensions in order to be able to speak to the controller. So, network virtualization. Network virtualization, as well, we've been saying with the slicing as well these days, is an enabler for multi-tenant networks. So it aims to ensure some sort of quality of transmission, quality of service, based on some sort of KPIs. But these things are things that are already provided by some sort of, by basically all the infrastructure providers and telecoms. So my point of view is that network virtualization came from the need of the different users in order to have their own infrastructure. So it comes as well quite close with infrastructure as a service and network as a service. And there are two different kinds of virtualization. So there is topology virtualization, which is being able to show infrastructure that does not actually exist, and control virtualization, which is the isolation in the control plane from the user to the device. So one example for of this need of manage your own infrastructure, we are working quite closely with BP and BBC at the same time. So we have one PhD student that is doing multicasting for video, is doing some sort of research with that. And BBC has an application that is called like this Studio thing, yeah. And so the idea of BBC is be able to distribute this software in different data centers, and then they are asking from BT to get more control over their own infrastructure, but at the same time, BT is saying like, no guys, we are managing our own network, and ask us for some sort of services we will deploy, and then there is this kind of discussion between these two companies. So, what network virtualization brings? Cost quality of service and transmission, traffic isolation, control isolation, and this topology simulation of virtualization. And how could this be done? In different ways. So you can, of course, provide some quality of transmission by providing a core, a wavelength, grooming the traffic over a single wavelength from the packet domain, modify with OpenFlow, for example, and fix the queues, and do these kind of things. And at the same time, you can remove the logic from a network device and put it in a software, which is what we call now network first virtualization. So, a first approach that we did some time ago was do network slicing. What network slicing meant to us at that time is a bit different of what we've been mentioning these 2 days. So it's not just the capability of providing isolation, quality of transmission, and this kind of guarantees for different tenants in the network, but at the same time, what we aim to provide is this control virtualization that I was saying before. So different users might have the visibility of some part of the physical infrastructure, and we will provide the capability of control what every user can control in their own network. So this was the approach of the Ophelia project. The Ophelia project, basically, let's forget about the application side. What it was providing was some sort of core in order to provide these virtual slices, but ultimately we had some sort of code, which I will explain later, that was receiving, acting as a network controller and open flow controller, receiving packets from the devices directly, and then being able to say, okay, this packet belongs to this controller and this controller. If a controller pushes some sort of configuration, check if it's allowed and that part of the slice belongs to that controller, and these kind of things. So, what is done? With a software called FlowVisor. So it's already quite old and it's not really stable. If you try to play with it might crash. It supports actually OpenFlow 1.0, and over this 1.0 we did the optical extensions in order to do this slicing with not just packet but optical as well. FlowVisor moved afterwards to other software called OpenVirtex. I don't know if you've heard about that, but it's a project that now is moving, but it has stopped already because they were planning to put it into ONOS, which is ORS being controlled. So now, after that, we move towards more, let's say, this not just optical, but the transport network virtualization, which is the Strauss approach. That image might be a bit misleading or a bit confusing because the start of how these things are written is not done exactly. So we have, of course, end-to-end orchestration. We have different slices or different modern slices for networks. We have as well this topology abstraction. We have different controllers, maybe TCE for GPLS enabled networks, and each controller could do this domain as another abstraction if they want. So we were having this kind of topologies, and we were working with this technology. So On the data plane, we were working with optical circuit switches. We have Olati, we have WSS as well, and Alba ROADMs. We have the OPS switches. We were working in collaboration with Japan, with the KDVI and Osaka University. We have different programmable NICs and with variable transponders. And we were controlling as well some sort of software from the IT side. And from the management point of view, we have different SDN controllers. We worked at that time with Ryu, at the beginning with Fox and Nox, and then Open Daylight. And in the last month, I think we did some tests with us as well. And at the same time, we have in this project that finished 1 month ago, the foundation elements for integration networks. On top of that, we have network orchestration based on the AVN architecture. And then we have some sort of network virtualization, which I'm going to explain later, with a module called multi-domain network hypervisor. And then as well some sort of algorithms. So actually the main work of our group was in the algorithmic part. I was talking before that with some of you that you knew Shutin, which was working in our group, and Ali that is currently working. They both have been working a lot on algorithms for virtualization. And then some sort of IT network management that I'm not going to explain now because it's a bit out of the topic. So this is the view of the Strauss architecture for network virtualization. We will have these different SDN controllers with what can be as well path computation elements. On top of that, the orchestrator. On top of that, the multi-domain network hypervisor, and the different network networks that will be controlled through different SDN controllers using OpenFlow. So first, the application-based network operations. It's an architecture composed basically by other modules that are predefined as RFCs, I think, like path computation element, for example, the virtual network topology manager, provisioning manager, traffic engineer database, these kind of things. And it aims to provide abstraction for applications, for network applications that we see on top. For example, OSS, NMS, or whatever other kind of network application. So, well, this architecture is composed by, first, I will mention just the modules that I've been working with. So the AVNO controller acts as a gateway for the applications in order to deploy, for example, end-to-end services, delete them, or manage other kind of events. The virtual network manager is used when we are using different PCs for each layer in order to have the visibility of the multi-layer connectivity. We have the main component of the architecture, which is the PCE, which can be active or passive, stateful or stateless. We have the OEM handler in order to monitor the network, the provisioning manager that has the information of all the interfaces in order to configure the network devices, and the topology module or traffic database in order to have the whole information of the whole view of the topology. On top of that, as I mentioned, we have the multi-domain network hypervisor. I won't go through the architecture, but what it does is it is able to receive a request for a virtual topology. This virtual topology is mapped logically to the network infrastructure, which is retrieved from the orchestrator. So the MNAs has the visibility of both the physical and the virtual. And at the same time, when this request comes and everything is mapped, the architecture starts different open-flow sessions in order to provide this visibility of the virtual network. So this is just like a more simple view. So I'm going to go through an example of how this architecture works. For this example, maybe it's a bit confusing, but I will use the same SDN controller, the same local SDN controller as the customer SDN controller, let's say, just to show in the same way that both topologies are seen and how the flows are mapped. On top of that, we have the AVNO, the multi-domain network hypervisor, and the same controller. And the interfaces, as I mentioned, it can be PCP or OSPF for the MPLS with a PCE. In this example, it's going to be OpenFlow. On top of that, we have BCP and BGPRS as well, and REST interfaces. In this case, there is some work that the project has been doing in order to try to standardize the control plane, let's say, interfaces, and is this COP, which is a control orchestration protocol, which is a young model that has been defined in order to provide common REST APIs for the control plane. So actually, now you can find it in GitHub. You can use it actually if you want, and it has been pushed into ONF as part of one project called Eagle, which is the aim of this project is try to standardize information models for the control plane. And for the example as well, we will use just one single domain in order to show how it works. So this is our local controller. At the same time, it will be the custom SDN controller. For this example, we use just a private domain. And that's the visibility of the SDN controller. We were using at that time OpenDaylight hardware version. And this is the visibility of the controller. This is the visibility of the ADN that we developed in Bristol. So it has the same visibility actually, and it is because we have just one single domain. And this is the format of the virtual topology request. In this case, to make it simple, we were just doing a request of a big switch network, so we will see some host attached to a big switch. And when this is done, the request comes to the multi-domain network hypervisor. It creates the visibility to the controller, and then the user will be able to control the virtual network. So this is the visibility. For this test, we were actually changing the IPs of the virtual host, because otherwise the controller would get crazy having the same IPs with different host running in different places. So it was just for the sake of running the virtual and physical infrastructure within the same controller. And then when this is deployed, the user can go through the OpenDaylight GUI and push a flow. So the way it's mapped is the user will push a flow into the virtual switch. This will be received by the multi-domain network hypervisor. It will map this flow into an end-to-end request that will send to the orchestrator. The orchestrator will calculate the path and will push the flows into the separate, in this case, one single LDN controller. So this is what we did. In order to simplify, one single flow was translated into a bidirectional path, which is not the best way of doing it, but it was just for the sake of doing it faster. So yeah, we can see here on the left the virtual flow and all the physical flows. And the delay, it was in terms of from the top to bottom, I think, if I don't remember wrong, in terms of hundreds of milliseconds, but it depends on the implementation, of course. And this is the visibility of the orchestrator, of the service. Actually, the ID is quite important because it's generated randomly by the SDN controller, and whenever this service is successfully pushed into the network, what this orchestrator does is report, okay, success, this has worked, but it reports the ID in order to allow the MNH to map this virtual flow into the end-to-end service. So whenever the user wants to delete the service, or the virtual flow in this case, it will be mapped into the end-to-end service and it will be implemented. So this is just another view of the orchestrator. As we were running a packet domain, we were running just a ping to show that all the operation work. Actually, this is what I meant. Just by installing the virtual flow, the rest of the flows disappear. Okay? So now I will change a little bit the topic, and now we move to data center and the data center part. So the main thing that I will talk about is about one project called Liveness, which was about optical data centers. But before that, I would like to mention a couple of our PhD students actually are working in disaggregation into the data center. So what they're doing is they are working more in the algorithmic part of, okay, in case you have a disaggregated data center where you have your memory, your CPU, GPU, RAM, whatever it is distributed, how to build physically your, in this case, optical algorithm in order to reduce the latency, which is very critical in a disaggregated data center, and at the same time, how to do the planning. So both of them are working in this kind of algorithm part. And then the other work is done by two projects. One is linear, the other one is cosine. Cosine is doing both optical and at the same time the required part inside the servers. But this project is more at the same time, I would say, novel, but at the same time a bit unrealistic. So it's nice to show this. So this project is about all optical data center, and you might think an all optical data center doesn't make sense. So my personal view is that, okay, it does not make sense, but the project itself is a good exercise in order to think what kind of advantages or what kind of problems an all optical data center network can have nowadays. So this is well, just a view of the architecture. I'm going to explain a little bit. So we have different racks with different servers. Each server will have a NIC, which in this case is, if I'm wrong, this NetPGA from Cambridge. And what the NIC can do is receive the incoming traffic from the server. In this case, as the FPGA will not be detected by the operating system as a network interface, we were doing a loopback. And then the NIC itself is able to detect the traffic and switch it and then send it across in two different ways. So the FPGA itself has different interfaces and can send the traffic through, let's say, OCS technologies or through OPS and tag the traffic with the required packet. Sorry, the required label for the packet. So this is the NIC part. Then on top of that, we have our optical cross-connect switch. We have as well some passive splitters. We have a WSS and different OPS switches. And one of the most important parts of this architecture is that all the devices in this data center, optical data center architecture, are OpenFlow enabled. So for each one of them, we build this OpenFlow agent, and then with this extension, we were able from the SDN controller to see all the devices and be able to reconfigure them. And on top of that, one of the things that we built for ECOC last time was a demonstration that was presented to us for the paper, where we had a virtual data center planner, which was a wheel where a user would specify some sort of requirements, and then when this virtual data center was pushed into our architecture, we were able to pop up a monitor app in order to monitor some sort of capabilities or some sort of things, let's say, from the optical data center, which is power basically and the OPS rate. We were exposing these two things, and well, this is the Wii. These machines, even though we were mentioning the CentOS, these kind of things, it was not into virtual machines inside the server, because the actual research that we were doing was in the optical network, in the optical data center network. So we have at that time bare metal servers, and the main thing that we were doing is mapping these multicast capabilities and the different technologies that the user wanted to use in the optical data center. This is the view of the way that we were showing to the user in order to monitor the power and the OPS rate. And after this, we were going to do some sort of more meaningful research in this optical data center in order to push in the configuration at the beginning protected services. So one of my colleagues did a bit of research. We were actually configuring end-to-end paths within the optical data center, but at the same time we were providing low priority flows into some of the devices, like or to do the further configuration when some parameters are detected in the optical data center network, and unfortunately it was rejected from ICO this time, so we are trying to push it somewhere else. And now I will move to our EPSRC flagship, let's say, project, which is TUCAN. Well, this image is from the proposal, the image on the right. So what TUCAN aims to bring are three main things. Well, it's quite a complex and quite a big project at the same time, but it aims to bring three main things, which is the first of all is convergence. The second is abstraction, and the third one is service orchestration. So out of these three main things, I'm not working in data plane, so I won't talk a lot about convergence, abstraction. Frederick Watt is actually leading that part, and I'm more involved in the PC3 or Web Package 3 part, which is service orchestration. So one of the things that actually appears there is virtualization. So instead of doing actual virtualization or the visualization that I was explaining before in projects like Strauss, what we are building is some sort of quality that might be confusing for the ones that come from the computer science side. But well, we think each domain we will be able to do some sort of network control. In this case, on or ODA, we are trying to see which one fits better. Then we will have some sort of infrastructure and energy management, which to some extent will be put in the same box. And then on top of that, we will have the TUCAN orchestrator. The TUCAN orchestrator, there are 4 boxes, but I will say that is more divided in 3 layers. We will have on top a service mapper, which will provide a catalog of services, and it will provide as well some sort of high-level interface in order to define the requirements for that service that the user has chosen. And then below that, let's forget about the performance monitoring. We will have an infrastructure as a service platform, which will handle, will receive this mapping of service to infrastructure, and will show to the user an infrastructure that might be the correct one or might not be. The user will be able to modify that infrastructure and push it into the network. And the other module is the performance monitoring, which we are actually now trying to figure out what to do with that, because if we are isolating the infrastructure from the user, in the sense that we are just providing quality of service and then we are just allowing the user to specify some requirements, if one of the requirements is, okay, we want to have some sort of information on my virtual infrastructure in real time, let's say, you should be able to monitor some sort of things through flow, optical parameters, whatever it is, depending on the infrastructure, and push it as quick as possible. So we are now trying to figure out what to build in that place. And other part of the infrastructure that we are trying to build from Bristol is, let's say, an infrastructure as a service platform. So we use as an example or as a thing to all the HCNFD platform, and is distributed in this way. So for each server, it doesn't matter for the data center, on each server we will have different infrastructure managers. It might not be required if, for example, if you are using OpenStack can orchestrate different servers in the same data center, for example. On top of that, we will have virtual network function managers, which in this case we are not developing anything about that now. We are trying to figure out some sort of protocols or information model, things like Tosca might be on there. And on top of that, for each data center, we will have a data center orchestrator, and we will have one main orchestrator that will provide a graphical user interface or RESTful APIs for if the user wants to build some sort of application on top in order to automate things. And we'll have the database of the users, of the virtual infrastructure, and resources that both physical and virtual that are used in the network. And on the other side, we will have a catalog of the images, both for DNS and for other purposes, like endpoints and these kind of things. And then by now, the test that we've been doing, we've been using ONOS in order to provide the network configuration, so we are doing both things. One is to follow the, I wouldn't say intent, but end-to-end approach. And the other one is doing this thing that we call policy injection, which means that you will set up some rules in the SDN controller that will be stored in the persistent database, and then when the incoming traffic is coming, the forwarding application will say some sort of things. I will explain later. This is just an example of the GUI. So far we've been playing with some sort of DNS, but we haven't done anything serious in the DNS part. So we are using OpenP switches, we are using some sort of, as well as OpenP switches and some sort of IP tables within rooms and this kind of thing in order to set up firewalls and this kind of things. We are trying now to use specialized hardware, such as some sort of FPGA that we have, in order to perform more kind of security services, like for the packet inspection. We can perform firewalling there as well, and this kind of thing. We have FPGAs from a company called Flerihan as well. So we are trying to figure out how to put remotely services there. And just to show an example of content that we've done so far, we have something as well as we have these different work packages. So one of the work packages in this project is the Tucan Lab, which is a laboratory in order to do this experimentation. So we have the 4 universities. We have Edinburgh, Lancaster, and Bristol, and we have all them connected through Janet. And one of the tests that we did, well, I would say a month ago or something like that, was connect from Raspberry Pi, which is acting as a Li-Fi client. We were using the Li-Fi devices from Pure Li-Fi, I think it's called, from Edinburgh, in order to provide connectivity from the Raspberry to different data centers in Edinburgh and Manchester. And at the same time, we were providing NAT service within a container in order to do the address translation and go out into the Janet network. I will talk about a couple of tests if I have some time that we've done in the context of Tucan for Bristol. One of them is integrating this ONOS SDN controller with some sort of pieces from the ADNO, which are the DNTM and the Layer0PC and the provisioning manager. And the idea of this is instead of bringing the whole complexity of an optical network into the SDN controller with ONOS, what we were doing is having a separate platform which is going to take care of the multi-layer provisioning. So, well, this is basically what I just said. And the scenarios that we used, we have isolated layers of networks. In between we have optical. So for optical, we were emulating a kind of fiber switch meta network, which was trying to simulate somehow the history of the network, actually. And the other one was we were using the MDFIS infrastructure, which is, if I'm not wrong, National Fiber Infrastructure Service, which is another project. And this is just a view of what we were using at the time, like this policy database in order for all this, the injection of services that I mentioned before. Then we have ONOS, we modified the forwarding application of ONOS in order to provide this custom forwarding. We have the virtual network topology manager, the protocol adapter or provisioning manager, we can call it in whichever way. We were in this test speaking or talking to the devices using protocols like the CPI, and in this case we were sending get messages in order to configure as well amplifiers, and the Layer0PC as well. So, this is the two scenarios. We're using the MDFIS network, which is shown on the left, and then on the right we have the fiber switch network and the MDFIS. And this is just the forwarding workflow. So when this new service is detected by an IP packet, ARP, whatever it is, we have this persistent database with all the services that are allowed. If the services are allowed, we perform layer 2 path computation. If this path cannot be found, we send what honors bill plus spanning trees from both source and destination, and it's sent to the VNDM. The VNDM goes from the source and destination to the leaves, trying to find a multi-layer path. If it finds it, it configures it. It computes it with, through the layers of DCE, and then when it's configured, it returns a success to honors, and honors waits until this new link appears in the layer 2 network through LLDP. So this is just some, well, basically one result, and on the right we are showing how honors this new link is popping up, and on the other side, apart from the massive orange or red drop, which is some delays that were happening in the network because of our Janet connectivity. We were having some issues reaching some nodes in the NDFIS network from the control plane point of view. The most important part is the part that takes more time, which is around 400 milliseconds, is the discovery. So the time that it takes to honors to figure out that there is a new link. And then the second test that I'm going to talk about briefly is about some, we put two different ideas together, which, well, actually we were in collaboration with BT. We were working with Andy working the idea of, okay, if I have a distributed data center infrastructure, how to transmit our DNS in a secure way. So how to encrypt the images and be able to transmit it to different data centers. And as we are working on a project called Quantum Hub, we were trying to figure out if quantum key distribution could be the solution. So the idea is, in case, imagine that you are an infrastructure provider and you are trying to send these images from one point to the other. You are sending, for example, a firewall, and this firewall is detected in between, modified, or whatever it is, and you don't realize that this is happening. So in that case, a full network can be compromised. So how do we try to handle this thing in quantum key distribution, which has a lot of advantages, but at the same time has a lot of restrictions, let's say. So with quantum key distribution, what you can do is to share these keys in a secure way, so then you can perform secure clean key encryption in order to transmit. So we were using at the time AES, for example, in order to encrypt our images. This is just an image of point-to-point image of what we were doing. We have there in the middle the QKD, what we have different quality switches. We have the quantum key distribution boxes. We have the key servers, which are the ones that are collaborating with the quantum key distribution boxes, and they are synchronizing some sort of things like filters and so on in order to generate the keys. And on top of that, we have encryptors and decryptors, and we have the orchestrator on one side and one energy stack on the other side. And on top of that, we were doing some sort of scheduling in order to reduce the cost of the deployment of a quantum key distribution network. So in this case, what we had was a really small network, let's say. We were reaching up to 25 kilometers. In order, if you want to reach farther distances, you need to go for the trusted node kind of approach and have a multi-hop encryption. But in this case, we were doing just one-hop encryption, and we have different clients, which are these nodes B, C, and D. And in order not to have a pair of quantum distribution boxes for this communication, what we did was have one single Alice, let's say, and then be able to synchronize with different blocks in let's say, in a time-shared approach. So this is just the workflow of how this was happening. So if an image is not found in the remote data center, how we get the key, how we encrypt, how we send the image, and how we decrypt from the other side, request the key, and decrypt from the other side. And these are just some results. As I mentioned, we went just up to 25 kilometers, so we tested back to back, 5, 15, and 25 kilometers. We were seeing different, of course, attenuations, different rates on the transmission of the key, different quantum bit error rates, these kind of things. And from my side, well, just one single more thing, which is we are currently working in different EPSRC phases, more than what I said. So both from the EPSRC and the European Commission point of view, these cross-project collaborations are quite well seen. So we are quite open to for any kind of collaboration. And at the same time, we have different infrastructures. So some of them come from European or both EPSRC projects, like NFIS is from EPSRC, for Fire is from, I think, from the European Commission. And we have as well in our city, Bristol is open. So in case you want to, both from the infrastructure point of view or from the project collaboration point of view, if you want to collaborate somehow, feel free to contact us, in particular my bosses. So that's all from my side. Thank you very much.
Alright, although I know all of you are eager to get coffee, I think we have time for one or two questions, if there are any.
So you mentioned somehow in the presentation of the app, you see you need an orchestrator for network slicing or something like this. So why network slicing will need a special treatment?
The orchestration, I think you are talking about the strong approach. We were not using an orchestrator for the sake of doing network slicing or network virtualization. We are using a network orchestrator for the sake of doing this multi-domain, this multi-administrative domain kind of control. So we need to orchestrate all these different domains from a single point of view in order to provide these end-to-end services. At the same time, one of the things that we were performing at that time was, okay, when a user asks for this kind of digital infrastructure and pushes some sort of end-to-end service, in this case flow that is translated into an end-to-end service, what we were doing is some with applications in the local domains inform the IAM handler within the orchestrator, which is the DNO, in order to perform reconfiguration without without making the user aware. Okay, so the user will keep its own configuration, but at the same time we were performing some sort of reconfiguration.
Okay, so the reason is the multi-administrative domains that will need this additional level.
So from the control plane point of view, that's the reason, and from the let's say reliability of the services, the virtual services point of view, that was more of the second thing that is.
Do you think that is a network service which is let's say that is not sufficient?
No, from my point of view, this HNLB architecture is more performing, even though it's networking, it's more performing in the network function virtualization point of view. So it's one of the things that I was showing is this new approach of Tucan. So okay, you will have this network function distributed, whatever it is, but then they need to be connected. So this way of connecting these virtual instances might be done by an SDN controller, or in case of being things that goes across different technology or administrative domains, they should be orchestrated somehow. So in the picture of the infrastructure as a service platform that I put, we were talking to ONA directly because we were performing in our lab, but then if you have this multi-domain kind of network, you should talk with orchestrator.
Thank you.
All right. Are there further questions? Okay, then let me thank Alejandro again. I think there's coffee served. sales. Yes. So, yeah, not this room, down here. We have one more session today on requirements and use cases, presented by Charles from Wireless. Yeah, so let's start again roughly at 4.